So you can look at some of the links. I'll be following them as much as I can, and some other things that I want. And I'm going to tell you a story. So where is the share screen button? 1 second. Here we go. Perfect. So let's start the introduction. You know me, I organize the meetups here, help organize them. And what I really do in life is I'm a computational disease modeler. So I'm not a medical person. I've no medical training from that perspective. However, I look at a lot of diseases and try to understand how they work from a computational point of view. Like numbers, I'm looking at the numbers. I used to work at the biostatistics department, but I'm computer science in training or in engineering training. However, about 10 years ago, I actually decided to take whatever I was doing there at the biostatistics and department and take it outside. I was a software developer and I took it outside and started developing the tools on my own. So I have a tool called the microsimulation tool. I'm going to show you how it looks like. It has a model and all sorts of stuff that you can model a disease. I'm just showing you the model I'm going to talk about later. And I started modeling diabetes. This was about 10 years ago. This is how a diabetes model looks like. My perspective, however, was different than anyone else in the field at that time. I started working on multiple models, not one model, because I noticed one thing. Everyone who has one model, this model is off somehow. And I've seen this enough times by then to know that one model cannot solve the problem. It's just like sometimes some problems you need multiple experts to solve. Same here. So I also started running the models on multiple populations. And the key thing, I was starting to add more and more computing power. So first I used like one desktop with 8 cores. And later on, I even went once on the cloud when I had some fun, just like small simulation in the cloud with multiple machines. But more and more, I grew in demands of power because what I was running multiple models against multiple populations to understand what really is going on. So what you see here is a diabetes model, and I'm going to show you some things, how things grew. So since 2012, this is the model count and some other parameters. So this is how many variations I actually have there. Validations I have. So you can see how the number grows, but look at the number of populations. This is how much I grew, and this is diabetes, not even COVID. But then how many equations, how many models I actually started plugging in. And you can see different types of equations. Now, later on, it became what's called an ensemble model. And then, and by the way, if you have questions or anything, just jump in, interrupt. I'd rather have it more of a conversation, just more than a conversation than a story. Eventually, this is what I was getting for diabetes. What you see here are actual clinical trials. And this is what you see now is the most validated diabetes model ever made. Most validated because I validated against more populations. But notice in this graph, the fitness score means the error, basically. The higher the circle is, the higher the error. And you'll see this graph in many forms later on. So this is something I wanted to show you first. Each one of those circles is a population. It's a cohort in a clinical trial. The data came from clinicaltrials.gov. I won't bore you exactly how it works, but the system here is trying to figure out what is the best models or best model combination that fits the data, and the data is clinical trial data. So what you see here, the circles, the higher the circles they are, the more we cannot understand. Those near the zero, this means we can more or less model it computationally, meaning we can have some equation that explains what's going on. And the bar on the bottom, the one that you see changed, is actually how much each one of the models influences the ensemble. So this is diabetes. I've been doing it for 10 years and got to the point that I add human interpretation. Human interpretation, we'll see it later, comes out with COVID, is like when some number, and medical numbers are not always accurate. I don't know, you can think about lab tests that always have an error or something like this, but it actually goes much, much further. It got to the problem of sometimes whatever is being measured is not defined in the same way. I won't go into details too much, but even in clinical trials, sometimes give you two numbers for the same thing. Just tell you, oh no, we measure this in two different methods. So eventually, you need some interpretation of the number you're seeing. And when we get to COVID, we'll talk about it in a bit more, but each number being reported is not always the same. So I added an element of like humans being able to interpret the number. So human number one interprets the number different, and therefore the error is different than human number two, than human number three. In this situation, this is like the experts are all me showing some examples of what some people might think about. But this technology allows you to take human data, computational models, and actual data that you find, and combine them together and see how well it matches. And improves that match by trying to figure out which team of explanations fits best. So basically, this is the reference model. It's called reference model because it provides a reference to how well we understand whatever we're seeing. It's also called reference because it was initially composed out of references. So this is still diabetes. And I'm showing you one paper that I published about this, and you can go and see this. And basically, this is the diabetes. I showed you it a little bit bigger. Notice that my plots are generated by, it's all Python, and the plots are generated by all of this technology. It's interactive. I can go in and I can look at each cohort, and it gives me some information about, like, for example, here it tells me the average blood pressure on this clinical trial cohort. But if you look at this graph, remember one thing, we can't understand all the numbers perfectly. And this is something I saw in diabetes, even if we take multiple explanations. And then COVID happened. So when COVID happened, we actually canceled one of the Python meetups, and I did some talk about some other things. But then people started asking me, Jacob, this is computational disease modeling. This is your field. What about COVID? What about COVID? What about COVID? So initially, my tools were not equipped to handle infectious diseases because infectious diseases are modeled a little bit differently. There is interaction between individuals. While diabetes, it's a chronic disease. It's just progression of the same individual, what happens to them in time. And the simulations are at the individual level. This is why it's important. So at that point, what happens that people are asking me so many questions like, how about COVID? So I decided to change my tools. And to help me with this, there was some hackathon at the beginning, and this is my team there at the hackathon. Some nice ladies helped me out, and you can look at some of the things that we've done there. But really what I really did is I converted my tools, the micro simulation tool, the tool I showed you before, to be able to handle infectious diseases. And then I started modeling COVID. This was about two years ago when COVID only started. It took quite a bit of time to do this. Now, this is the first publication of the reference model that I found, that I published, and it was a very basic model, not even an ensemble. This is just kind of a test run. There was 2 mortality models. This was the big thing that's still an ensemble, But here I was trying to model COVID and saying, this is COVID, this is how it looks like. Using the tools I have, how am I able to explain what's going on? And I was trying to deduce what's the chance. One of the things I was trying to deduce is what's the chance of actually a person who's infected per encounter. If you see the person, what's the chance of transmitting this disease to another person? To do this, you have a lot of information you have to plug into the model. A model like this is very, very simplified because there are many, many things behind it, many equations. So I won't bore you too much, but these were the results. And I can tell you the number, the first published was this transmission. And it was 0.5. Second, oops. Iteration 4 was the kind of like the best results. 0.6% of probability of transmitting the disease. If you per encounter per one person who has the disease. So it doesn't seem a lot. What do you think? How accurate is this number? Come on, say something.
Jacob, did you consult with the epidemiologist?
I consulted for epidemiologists for years before. I was in biostatistics.
Okay, real good, real good. I'm just trying to understand.
I was in a team, but the thing is, none of them. The approach I had is quite different because they all came out of different. They all came out like the people who were in the field. They were like statisticians, actual doctors. The field is called health economics. There are many people who are doing things like calculation, like quality of life calculations. There are many, many subgroups there. But no, the question is whether for this model I consulted with anyone. This is something that I started doing on my own. And I started later consulting with more people. I'll tell you the story. It will continue the story in continuation. You'll hear more about what's going on. But for now, just to tell you, I started with running this. It came to the point that according to all the data that we have, that I plugged in, it was 0.6%. Now, what is the data that we have? Let me show you how the data looks like. I had one of the big problems is getting data. Oops, this is not what I want to show you. Here, this is data from the COVID tracking project. Just to give you an idea what I'm actually following and why am I what's going on there. So the numbers I'm looking at are actually numbers for the US for each date, and they have number of positive. Positive means test was positive. It doesn't mean that like you know exact number of infections per state, but this is the number of positive tests reported, this number of negative tests reported, and you have number of deaths here and even recoveries. Those are numbers reported per each date and hospitalization as well. And here's death. This is a long file, but this is actually what I'm trying to match. Because I'm saying if we computationally could explain whatever is going on, we should be able to match those numbers if those numbers are correct, and we'll talk about correctness later on. So I hope it gives you an idea of what I'm trying to match. And let's look at this graph here. It will repeat itself multiple times. Each circle here represents a state or a territory from the US because I have the data. And each circle tells me information about it per each time step. In here, each time step is like I had 3 time steps and like 3 months, 2 months, 60 days, 30 days, and the initial. I believe these are the numbers here. Sorry, here I have only 2 time steps that I'm comparing, 30 days and 60 days in this simulation. So I'm trying to explain 2 months at the beginning of the pandemic, and at the beginning of the pandemic, this is all the data that we had. So I took 2 points in time, and I'm trying to match them with multiple models. We'll talk about the models in a second. I'm going to expand them in a second, but The models, sorry, here I had only kind of one model with multiple parameters, and I was trying to compute what are the parameters. And I took into account like population density and the transmission coefficient is the one that's
and this is evolving.
What's the chance of transmission?
This is evolving from the diabetes. You mentioned first is diabetes, and then then the COVID. Yes, sir.
The technology is from diabetes modified towards COVID. The data for this has nothing to do with diabetes.
Yes, sir. Yes, sir. I got you. I'm just trying to understand the model theory is started from diabetes and
the tools, modeling tools. The simulation tools require quite a bit of computing power. I showed you graphs before. Yes. So there's like, it takes quite a bit of computing power to compute this. I believe this was about 6 years of computation altogether. And for this, I got, actually, it's now maybe a good time to actually say all the people who supported me, not only on this work, but for the last 2 years, there are many organizations that gave me some computing power. So there was Rescale that gave me, that got some money from Microsoft Azure and Amazon AWS. They provided computing power to run those simulations. Those simulations quite a bit of time. Like I'm running it on like hundreds of cores. Wow. For extended periods of time. So it takes like simulations take a day or at least a few hours, depends how small or how big they are. And also later on, I got, you'll see the data later, you'll see the results later. I got some funding later from Midas. Midas is actually funded from the NIH from a program called STURDIS. So Midas is a network of modelers. You can look it up later. And many modelers go in a model there. So I got funding from Midas to do a big simulation also. So those provided me with computing power. Otherwise, my computations are being made on a 64-core machine that I have at home here. I now moved it to Israel, but like there's a 64-core machine that's even now computing COVID data. Simulation takes weeks sometimes. It depends how big or small. So I remind you 0.6% the chance of transmission. This was a while ago. Now, after Midas gave me some money, I also joined, there was a working group, and you're asking who am I talking to? I'm now working with many scientists from all around the world. We actually just published a paper, it's unrelated to this, but about all the problems in modeling we currently have. It's in Frontiers in System Biology, just published last month. It took a year to get this paper out. But there was a big working group now, viral pandemic ones. But beyond that, I'm connected to the Midas folks. And because of what the Midas gave me some money, and because of those interactions, I was able to go ahead and improve my model. Now it became an actual ensemble model. Ensemble model means I have multiple models that are coming from multiple sources in the literature that are running, and the system is trying to match them as best as possible. And so in this specific one, let's show you some of those. These are infectiousness model. Oh, by the way, what you're seeing here is a publication. You have it before. This is, as far as I know, one of the only interactive publications we're able to publish. Publishers today cannot publish interactive papers, ones that you can actually interact with the figures. Very few are starting to do this, and even the scientific publication system cannot handle it. But I was able to receive a DOI from a company, small publisher that was nice enough to allow me that. So basically, what you see here is the model. And notice you have multiple models now. You have multiple infectious models. I'll show you what it means. Multiple transmission models. You remember that number that I told you before? Now we have multiple of those competing. We have response models. Response models, how people behave, how do they respond to the pandemic? Basically, those are behavioral models. There is only one recovery model, but the recovery is not something that since I'm modeling the beginning of the pandemic, it's not very important. And then there are multiple mortality models. I'm going to show them later. Now, notice I can interact with the paper and you have links to it, but those are the infectiousness models. And they come from multiple sources. Actually, maybe it's a good time to tell you where I got my models from. I'll name some people. So it's not in particular order, but I have them written down here. So Lucas Boettcher gave me 2 models, actually infectious models and the behavior and the observation model. I'll talk about this later. Robin Thompson and William Hart gave me an infectious model. Then Kay and Perlson gave me 2. They actually published it, but they talked to me about it. So they have 2 of the models are of infectious models are from them. Eric Ferguson later gave me a behavioral model, has to do with state closures. I'm going to show you the data later. And Felipe Castiglioni provided the mortality model. Other models I pulled out from multiple sources and combined them, and some of them are my own assumptions after doing this for a long time. So here I'm showing you 4 of the models. Later on, we'll see more. But these are infectious models, meaning at day 1, when the person gets infected, how much are they infectious compared to their max? And usually like day 3 or 4 are max, but some models say no, they stay at max infections for many days, 3 to 11. This is one of the models I pulled out from the literature. So we have transmission models. Now we have parameters, not only the parameter of what happens per one encounter, but also includes the population density of the area, of the state, and some other things like, oh, in random something happened. Response models, these are examples of response models. I won't go into details, but basically they say, some of the response models say people don't care about the pandemic, they behave like usual until they get hit. So this is one response model. Other response models are, I took information from Apple mobility data, which say, okay, how people mobile, according to how much people are mobile, this is how many interactions are there.
Quick question, is this modeling all COVID cases throughout all time, or is from a specific day to a certain day? Because maybe in the beginning of the pandemic, the infectiousness was different from maybe when they had the Delta variant, so on and so forth.
Okay, well, we're talking at the beginning of the pandemic. There isn't even a recovery model proper. We don't look at the recovery model. The recovery data is not being even compared, because I'm looking only at the beginning. Because the idea is that if you have a tool like this at the beginning that can explain the next pandemic, this is where the power is. Because the numbers will appear in the next pandemic again. But if you have a tool like this in place that tells you, oh, the pandemic behaves like this, that maybe the officials who are making decisions may be more informed than what they were before. Because at the beginning, the data came from the came from the COVID tracking project, because I kind of quote what they say. It's like, because no one else does this, we did. It's paraphrasing. It's not exactly what they said, but basically this is correct. I was searching for data at the beginning of the pandemic about what's really going on, and they were the best source.
So what is your definition? Sure. What is your definition for beginning? Do you mean,
beginning,
March
I started
2020?
modeling around April, which is a few months after. Also, you have to understand, like, you have to have enough cases to capture it, because rare events is something that is very hard to model, but you have to wait until the pandemic gets to the point that it's no longer a rare event, and you can actually have enough instances that you can actually compare to. So,
sure. So are you talking about like global? So are you talking about global, like October?
Oh, I'm modeling currently only the US because I have US data, but I can tomorrow go global because the data now exists. Now I can go back in time and go exist. We'll talk about this later.
So what specifically, like January to April of 2020? Like what exactly
So
is the
it
date
varies
range?
between publications. Some of the publications are this one. The Curas is actually from April 1st to June 1st, but later on I changed it.
Okay,
You will understand why. Wait for this.
okay.
Wait.
Because it varies
Okay.
quite a lot, so just wanted to ask.
What? Excuse me?
This data varies quite a lot from the beginning
Oh,
towards the end. So,
yeah.
these numbers don't really mean anything unless you know exactly the date range.
Oh, you're getting there. Wait. It seems you're very passionate about it. Wait to see it till the end. But yes, bear with me here.
I got one more question. You can tell me I have to wait, but we've had different variants. And can you see any time variation in some of those? Like if you think about the
Greg,
variance.
this is the big, I'm modeling the beginning of the pandemic. One of the reasons I'm modeling, I'm trying to get the numbers right. Tell me at the end of the talk whether the numbers are still okay and whether we can still explain. You tell me, okay?
Okay.
I'm throwing this on you so you'll understand exactly. I'm leading something with this, but wait with me. It's like,
right,
but
yeah.
the idea is to explain if those numbers are. I'll give you the pretext. If those numbers mean anything, we should be able to explain what happens computationally. If we can explain this logically as humans, we should be eventually in any way explaining it somehow computationally with computers. Correct?
All right, I'm going to
Is a
keep
fair
listening.
assumption?
Yes.
Good. So this is what I'm trying to do. I'm trying to explain. Some people try to predict. They tell you, oh, we predict. Some people are more actually saying forecast. Forecast is a better word because they say, okay, we forwardcast whatever we were thinking for in the past and we try to project it to the future. So forecast is a little bit better. Some people say, no, we can predict. We will see whether we can predict or not at the end here. And go back and look at all of the literature, thousands of papers, more than thousands were written about this, and you'll tell me. But I won't. Let's wait with this. The question you were asking before, this is what I'm showing you. This is not Curas. This is later on work I did for Midas, and then I had all those models. You see all of those blue bars here? Those are the infectiousness models, how much they influence. The green ones are the transmission models. The response models had only 3 at the beginning here, and then eventually all of those are kind of mortality. Mortality is kind of complex, but those are all mortality complex. I won't go into the mortality unless you force me to. But all of those came from sources or multiple sources, and I haven't seen you the mortality. I'll just show you the mortality. This is Filippo Castiglioni. He actually, from one of this working group, I said, look, I need a model that actually tells me what's the chance of someone at a certain age dying in a specific time. And this is how it looks like. This is from the beginning of infection. This is the time. And he actually did this by trying to figure out how cells in the body, what's their chance of dying once they have, like he was saying, like, because how much damage to the cell, and at some point the organism so much damage that the organism dies. So this is how he calculated it. Now notice, this calculation came from the cell level. Not at the population level numbers that I showed you before. He did these calculations at the cell level. This paradigm is called multi-scale modeling because you have different scales. You have scales in the organ, in the molecular level, at the human, at like a one-person level, I said organ, and cells, of course. So this is like a whole scale of modeling, and the modelings from lower scales now we're able to pick it up. So what you're seeing now is the first multi-scale ensemble model for COVID-19. Because there are multiple models, therefore the ensemble, and multi-scale because some of those models came from different scales. So this is how one mortality model looks like, but the others are much simpler. Anyway, let's go back here and look at this. And someone was asking about what am I modeling? Again, I'm modeling day 1 here is April 1st, but here I'm from April 1st to June 1st, and I'm able to model it. And my system kind of optimizes all the models and tries to figure out what's the chance of each model being accurate, more accurate, less accurate. So I found out that the 0.6% of transmission wasn't very good. But you see this model that dropped and disappeared? This is 10% of transmission. If this model is being eliminated by the system, it tells me it doesn't match the data. So this is probably an overshoot, but the other models kind of cooperate. And you see all of those infectiousness models, they do still influence whatever happens at the end. And you can actually go and see how each iteration, I started from somewhere like this, you can see how those circles here drop towards the ground. Remember, we want them as close to zero as possible. This means this combination of models is better. Think about it as a team of models, like a football team or whatever. And the question is, do they cooperate well with each other, and which player should play or not play? Okay, so now this happened before, and I'm going to skip some things. Midas later on, we added some more models, but let me show you. This is the future work then. This is the first time I started reducing the number of time I actually, this is still 60 days. My conclusion was that we are unable to explain 60 days of time, because even if I ran the best models, eventually you can see all those jumps between some states. The numbers are way off. Some of them are pretty good, and most of the time they were underestimating all of the models were underestimating just to match the numbers, meaning they were reporting less deaths and stuff like that. So
yeah, one of the things, sorry to interrupt you, but one of the things I found out for New York City is that it takes about 1 to 2 weeks, up to 30 days for them to actually report a death. And when they report a death, it's very unclear whether or not they're going to mark it as COVID or not. So the death count was never very accurate, and you're always up to 30 days behind on the death rate. That's why it's so difficult to do a 60-day model.
Interesting. You were not the only one who was saying all sorts of things like this. So this is where exactly leads me to the next thing. You remember I told you about diabetes and I added a human interpretation because the numbers were off there? At the beginning, I told you, I showed you this paper here. This was published before the pandemic. And actually what you're saying now is exactly that. So you're telling me, oh, you cannot believe the numbers, correct?
Yeah, correct.
Am I interpreting whatever you said correctly? Good. So let's jump into the, I lost the correct, here we go. I think it's correct. Yeah, this is the correct one. I think, no, this is not the correct one. This is the correct one. Good. So look at this. You see those purple bars? Those are observation models. You're telling me New York is off. And I'm asking you by how much is off. You're telling me if I report a number 5, then it should be 50. I'll tell you more things.
I can tell you that I don't know how much the number is off.
No. I know. This is, Lily, we're good. We're good. I'm trying to tell you we all don't know. However, some people tell me, oh, this number is off by that. One of the numbers that's like actually the infectiousness number, you're talking about the deaths. The death is something that is easily measurable because the person died. But infectious is like, did you test the person? Did you test only some of the population? Is your test accurate? So even the infectious numbers are off. So you have numbers of infectious that are off, meaning they don't represent the really infectious level in the state at a certain point of time, because you don't know whether a person was tested or not. And also the death is off. So those numbers you're telling me are off. And I agree with you. So the way to correct it is actually add observation models. The observation models go and look at the number, saying, nah, this number is not that, multiplied by 5 or by 10. And each model, each observation model can be different. Let me show you how it looks like. This is an observer file. So it tells me, for example, that for Alabama, you have to multiply it by 715, and the number of deaths should be 1.1 more than whatever is being reported. This is something, for example, that Lucas Boettcher, he actually had claims very similar to yours. He said the numbers are off, deaths are off, and he actually contributed this to, and he told me, no, those numbers, use those numbers and see whether this model is better. His model is only one. I tried multiple other assumptions because I don't know whether he's correct or not. And several other people said other things. So the observation models, the first observation model here, the first bar, the purple bar here says the numbers are okay. If you say the number, if you report a certain number, no, this is the correct number.
Hey, Jacob,
go with it.
Jacob, how do you come up with those numbers? Like you show that.
Oh, you want to read the paper? The sources for them exist. Like many of them come from multiple sources, and some numbers you don't know. So this is why you have a model. The model will actually compute them for you. You can throw in multiple assumptions, and the system will balance them and tries to optimize them to fit as best as possible. That's the idea. The idea is that, okay, we don't know, but if we have the ability to check and use computing power, then the system will tell us what fits best. And not only one thing. Think about it. Models are assumptions. Model is not true. Someone tells you, my model tells me this. Even like weather models, like they won't always focus what will happen very accurately. Same here. The idea is that if you have enough assumptions, some of them working together can collaborate better. And this is where the power of this technology is.
Like, what is the correct data that you're comparing against?
So the correct data is whatever was measured by the COVID tracking project after it's being observed. The observation models will change it. Because remember, the observation models tells you, no, I assume this number is incorrect and off by X. And different people will tell you different things. So for example, Lucas Boettcher gave me one of those, but several other, I can tell you, like the CDC says the number is off by 5, the infectiousness number, the infectious number. We can find it at some point, but everyone knows, epidemiologists know that the numbers that being recorded are off because you didn't check all the infected persons. So well, you have to multiply it by some number. So
well, what I know is that, like, the death rate of 30 days before is more accurate than death rate today because there is a up to 30-day delay around that amount for certain governmental sort of systems to take place in terms of tracking the death. So are you also looking back in time and getting those COVID tracking project numbers back in time, like a month ago?
I'll go back. COVID tracking project numbers that we're getting initially, this is my ground truth, saying I have to match that. Because you have to match something. And whatever tells you something, this is my apparently ground truth. The question is, how can you explain this ground truth? How did they get to those numbers? And you're saying, no, your observation model say, don't look at the current number, look at the number forward or backwards in time.
Yes, that's correct.
Correct?
Mm-hmm.
This is what you're saying. So we can program this. But and then for each number, I can actually tell you for each date, no, look at the different number. I can actually program this. If you have this thing and you can compute it, and gladly I can take it. But then the question is how this model will behave, and we'll talk about it later. Let me progress. Otherwise, it will take us hours. But for now, everyone, I hope, understands to some degree what's going on here. And the observation models are important because, however, are they important or are there other things? So what I'm showing you now are results, recent results for a few days ago. I think here, beginning of April. Here I have many more models added. I have two more models. Two of those more behavioral models are added by Eric Ferguson. We was looking at numbers and we couldn't match them multiple times. So we said, okay, let's try to figure out whether state closures had anything to do with it. So he gave me a file with state closures. He actually did this, and I'll show you which one of those. Here, COVID lockdowns. For each state, when the closure happened and whether schools closed, restaurants closed, and blah, blah, blah. All of those became two models in this ensemble. Behavioral, how people behave, because how they react has to do with the fact whether things were closed or not. So those are those two models. So now we have 5 behavioral models. Also, I added Lucas Boettcher, gave me another infectious model later on. So this is the 6th one. Actually, I'll show you how they look here, called the infectious models. Here, those are the infectious models I currently have. So they're all now in one, and you can see they're quite different because different people behave differently. So the system will try to compute how many of, or how much of the population actually reacts according to each one of the models that were plugged in. Back here, yes. And then I added the 5th model here says it's a model, it's the observation model that should match according to the previous simulation I had, one of the previous simulations I had. Meaning I interpreted the numbers, I kind of skewed them off just to match them to see if it matches. Let me run this. Oh, one more thing that happened. I replaced model 2 and 4 in transmission. Those now have to do with the temperature of the state in that month, in that month of April. We took the information from NOAA and checked out because we were noticing that like cold states and warm states are kind of behave differently. So I added actually the temperature and see whether
the temperature constitute an ensemble. What's an ensemble? Sherry asked, "What's an ensemble?" What constitutes?
Ensemble is like it's a choir. You have many voices in a choir. So each model here is a voice. So now the question is how much you hear each voice, and those are the bars here. And some voices have specific, like they do specific things, like those are infectious models. So those are infectious voices about infectious, like people with opinions about infectious, but it doesn't have to be people. It's kind of like models. It's computational models. So maybe I'm mispronouncing it right. I know if Dylan is still here, he pronounces the word better. Dylan, you're here still here?
Yeah, I'm still here. I think
Okay.
you're pronouncing
How
the
do
word
you
ensemble
pronounce
just
ensemble
fine.
properly?
No, it's ensemble. You got it.
Okay. So I did get it. He was showing me how the correct pronunciation is, but ensemble is a choir of models. And the interesting thing about it, and it's interesting, and Dylan, for example, he works with machine learning a lot. Many of the models there are not intelligible. Those like this neuron over here, like fired, and this is why the result is, and no one knows really why. Many times, sometimes they can explain, some knows, but many times they cannot explain how the model behaves. It just kind of works. So people look at it as magic.
Does the ensemble?
Interesting. Yeah, wait, David, let me finish the thought and then ask. So,
yes, sir.
In this sense, in this model, everything is intelligible. I'm using machine learning techniques used for machine learning, but here the models are intelligible. You can explain each one of those bars, how it was computed. It's not like a black box. So it's human comprehensible. So you can try to explain, because really I'm trying to explain what's going on. So ask your question.
Yes, I was trying to ask if the ensemble minimizes the Heisenberg effect.
You'll have to go into the details of the Heisenberg effect, but what it tries to do is tries to improve the fitness. And to Lily, before she asked about, I think Lily asked about before this, what was the, what am I trying to match? So I'm trying to match both the number of deaths and the infectiousness, however, in different rates. Previous simulation, I found out that I could not match it very well, the infectiousness and the death. And I had a problem, and this is a serious problem. To match the deaths, you need many more simulations, and I don't have the current computing power. So what I'm trying to do in this simulation, I switched. I'm trying to match the infectiousness levels, and the deaths are also, but not as much. So I'm relying much more on the observation models. But interestingly enough, if you actually see what happens, if I drag this, you can see the models affiliated, for example, with temperature disappear. So probably nothing to do with temperature. This is the second simulation I'm running. You see the observation models, they are more or less not changing, and I'm not sure why. This is something that I still have to explore in future simulations. But you can see that what you see here is the total fitness for everything. And if I drag this from the beginning till the end, again, you'll see the system kind of improves everything. And you can see some states, if it yields to one state, the other one like kind of competes with it. So it's like, so you can see it's like if the models try to fit one thing, it has a problem. So here I'll show you what it happens. Like, look at New Jersey and Louisiana. You see, New Jersey, I can tone down New Jersey in very small, but then it will affect Louisiana. So some of the iterations, this is what happens. This is the optimization. And here I'm optimizing something like number of deaths plus number of infections. I mean, the differences between those two. The difference between number of deaths plus the difference between number of infections. A function of those. This is fairly recent results, and I can show you here. Let's look at the bed states. If you look at one of those, here I'm modeling only, Lily, you were asking before, here I'm modeling only 3 weeks, 21 days, because 3 months were too long. So I'm trying only to match the first days. And let's look at this one, for example. So, and notice I'm now, there's something called observed infected rather than infected. So you see the number here is off. The model is underestimating. You see 1.56 in observed infected out of 21.06. This is out of 10,000 people. The simulations always are 10,000 people per state. And when I run this, it tells me, oh, the model underestimated a lot. And this is why you see this jump in South Dakota. It tells me, according to the model, it should have been much more. This is South Dakota, but let's look at something that's compared a little bit better. Let's try this one. Here, California. California, it's apparently now fairly well modeled, as much as can be. So the observed death is about half. Not that bad, and the observed infected is actually kind of okay, 6.56 compared to 8.41. And I can actually show the results. I'm using HoloVis technology, so I can actually go ahead and show those per state, exactly what's going on with all those curves. I won't go into this, but I have those capabilities. And this is what you see is the average infectiousness curve according to what I was calculating. Remember, I have the basis functions that tell me each one of those curves I built from. These are the base curves, and it tells me if you combine in this way, this is how it looks like, the infections. So apparently people, according to all the data, are infectious for quite a while. Mostly infectious are like day 5 and 6 after infection. But this is according to all the things I plugged in. This is what I'm seeing now. At this point, I cannot tell you what's like the correct thing, because you remember I started like 2 years ago. I got to the point that I estimated the transmission rate was 0.6. Now it's more like 2 something, like the chance per encounter of transmitting disease. So my numbers were off then. I'm still to the point that I cannot explain things fully. This is the best I can explain it now. It doesn't mean this is the correct thing, but it is better than I was able to explain before, and I can rule up some things. So one thing I know, for example, according to all the data at the beginning of the pandemic, what we had, I'll show you the second model. Second infectious model was something which was long. So it probably tells me, look, the infectiousness time is much larger than people thought before. Maybe. Saying maybe because it still needs to match. But at this point, I would like to kind of like ask you what you think about it. But before that, I want to tell you why I'm doing it again. I'm trying to take computational tools that will explain the numbers we see. A doctor doesn't really think with numbers all the time. They do look at your charts and blah, blah, blah. But eventually, I want computers, I want this cell phone to have, to be your personal doctor all the time. And to get there, we need to understand all the numbers we're collecting. Currently, all the numbers are organized in clinicaltrials.gov from clinical trials. COVID is great because now we have a lot of numbers about COVID. The question is, can a computer understand those numbers and tell us something about the disease? If I'm successful in doing this, or at least get close, then we may at one point have computers, computer doctors all the time. The question is, how long will it take? Well, it took chess for computers to learn chess took 50 years. For driverless cars, we still haven't have them fully, but 40 years since they started development, you can see the timeline. And well, it will take quite a while with medicine, assuming that we start now, maybe 50 years, maybe something else. I actually ask people about that and they give you different answers, different experts. So at this point, I would like to yield and give the time for questions, and I'll be happy to answer, but this is currently what I have, and I want to make sure that I have not forgotten to thank anyone. So I thank all the people, and I thanked all the people who gave me money to run simulations. So I think I'm okay. Any more questions?
Yeah, thank you. It's never easy to make this sort of prediction. There's so many different factors. Sometimes it's government regulations. Sometimes it's, especially in larger, like states with a larger population, the infectiousness rate in a dense transportation hub is going to be much different, obviously, from when people are at home or in a suburban area. So there are so many different dimensions. So it's very interesting to me to see the many different dimensions that you've been able to map. So yeah, thank you for sharing.
I'm able to add more. If you have something specific, send me an email. I'll plug your models in. I have no problem.
Yeah, I had done COVID modeling as well, but only on a New York City basis, because my personal belief was that I only cared about, like, we only care about ourselves, right? Like, I only care about whether or not I should make life decisions on whether or not to quarantine myself back in March of like 2020 when it happened. So I only cared about New York City. I only cared about specific counties, specific zip codes, and the data that was published in that city. And then I started comparing worldwide, because it doesn't really matter, what those dots, I can see going up vertically. If I don't really know if that dot growth is exponential in the last, 3 days versus, not so much growth. So the way I was modeling things, I only cared about like my locality. Like, for example, the hospitals will publish like how many people around my age range actually passed away, and it was something more like 1 to 3% if they even were hospitalized. So that, then I could see specifically based on my demographic, my location, how it actually affected me. And that's what I cared about. That's the way that I kind of approach the data. And so it's always interesting to see, I've thought about this idea of ensemble models, but I didn't apply that for what I was doing. I was fitting some data into the population curve like everybody else was doing. And I was only able to predict in like future time, maybe like 4 or 5 days, just by manually fitting the population curve based on all of the history, and I always looked at all of the history versus, the last like 30, 60 or whatever days. And I still could, yeah, I definitely like could not predict very much because, there's also like, government regulations, even like whether or not it's a weekend fluctuated the data because, people get less or more efficient if it's a Friday versus a Monday. So it's incredibly difficult.
This is where big data comes in. Yes, there are fluctuations, but overall, if you have enough data for each day for a long time, overall, the mass of data becomes so large that you should be able to explain it. And by the way, this is New York. I'm showing you how well the model predicts New York now. Look at the observed death and observed infected. I'm showing you 0.21, 3 weeks into the future from April 30th. This is currently New York. This is New Jersey. New Jersey is a bit off, but you see it now?
Yeah, I think, the thing on people's minds for anybody doing time series was like, it's so hard to predict like giant events. Like everybody who was running like a, e-commerce type model couldn't predict COVID, and everybody had this big dip in, their time series prediction when COVID happened. So when everything's fine and good, I feel like it's easy to predict how things are going based on historical data, but it's so hard. Like tomorrow there could be a government regulation and it could change everything. And that's why it could be so hard.
Yeah, so forget about hard, and yes, I agree with you, but I've been doing it for a long time. And I've been doing it for now, maybe 15 years, disease modeling. So I've seen it all, and I can tell you what you experience is normal. No one can predict. Actually, I'm from Israel, and now I'm in Israel, actually. I'm talking from Israel. In Hebrew, we have a saying, "Hanevuah nitna leshotim." I'll explain. Prophecy was given to the fools. This is almost the direct translation of what I just said. It has some religious reasons why they said that, but basically the idea is that prediction is not something that humans should be involved with. That's the idea. And indeed, I've seen so many times people cannot predict. So I'm no longer trying to predict. At best, I'm trying to explain. And currently, this is the best explanation I have. And remember, I'm trying to explain the past rather than project into the future now. At the beginning of the pandemic, people were trying to predict what will happen in 2 weeks and stuff like that. It doesn't work that well. And then later on, you can see scientists blaming other scientists for having this bad model at some point. This is not the way we should actually handle it, like point fingers. We actually try to understand why can't we explain the numbers. If someone can explain the numbers, then with an ensemble of models, that's okay. Now, by the way, one of the reasons you couldn't do the ensemble is very simple. I have two US patents on this technology. So anyone in the US who's doing the same thing as me kind of has to get permission from me. It's kind of, but that's the truth. I have 2 US patents. I got the second one this year. Last year. I forgot, but it takes quite a while to get those. So, but yeah, I agree with you. Modeling is hard, and Python is very helpful. So just to give you ideas of what Python helped me, the micro simulation tool is all Python. I run Dusk to run my simulations on the 64-core machine, and I ran them on the cloud, on multiple clouds, multiple cloud platforms. It works beautifully. Holoviz is what is now shows you the results here. It allows me to explore the information and see what things are off. And some of those plots are really, really useful. The ability to hover something and see, oh, this is off, and write those. It takes quite a while to build this, but eventually it's very, very useful. And I don't want to bore you much more, actually. Unless you have questions you want to be recorded, we can stop the recording. Anyone with questions who want to be on the record?
I have a question. So you said you're in Israel now?
Yeah.
It's 5 a.m. there. I want to really thank you. This is amazing that you stayed up in the middle of the night to give this presentation to us. So I want to double thank you, triple thank you.
No, Greg, I want to thank you for being so consistent. You always come to those meetups, and this is why I'm up for 5 a.m. because of people like you. We've been organized. I've been doing this to replace some. It's a replacement talk currently, so it's like we've been organizing the Python meetup for people like you. So thank you for thanking me, but I thank you more than coming here again and again and again.
I guess we all win then.
Yeah, I hope we win. I hope we win.
Yeah,
We'll see. This is one of the communities I like, so this is why I'm here, and I hope you like the atmosphere here as well.
Yeah, so Jacob gave us a talk from the future. He's actually, I think it's April 14th there, right?
Oh yeah, no, yes, yeah. Oh yeah. I like this. The talk from the future.
So then you say there's no predictions. You already gave us some predictions.
Great fact, huh?
Well, thank you, Jacob. I think I'll stop the recording after this, but thank you so much. Really appreciate it.
Yeah.